Right. Oh, come on, come on, come on, come on, come on, come on. Right, okay, so let's just redraw the info here. You have your seesaw, correct, yeah? And then this side we said was 40G, and this side was 30G, and then in the middle was a 100G, and we'll put the turning point here, okay? And we are calling this distance here, that's x. This distance here is 2.5 minus x. And then, yes, that's right, isn't it?
Yeah.
And then this distance here is 5 minus x, because actually the total is 5 minus the x here. So, clockwise, if this is the turning point, can you see that this one is anti-clockwise? This one here is clockwise, and this one here is clockwise. Do you know what I mean? It makes it turn clockwise. This one makes it turn anti-clockwise. Can you see that? Yeah. So the first one would be 40 times 9.81x. That should equal 2.5 minus x times 100 times 9.8 plus 5 minus x times 30g. Now what's nice is there's a 9.8 in everything. So that goes. That's 40x equals 250 minus 100x plus 150 minus 30x. I hope that I have that okay. 130x minus 40x, is that 90x equals 400? Cancel, x is 40 over 9. Is that right? So, no, I think I did something wrong. That seems a bit too big. Did I miss a number somewhere? Can anyone spot it?
107.
Which one?
Negative 100 and then negative 30, so it should be.
Minus 130.
So
Oh, sorry, when I took it to the right, plus 40, so it should be 170x, isn't it? Equals 400. Yeah, so what do we have? X is 40 over 17, that's better. 2.335 meters. So, the father, he had to move it 15 centimeters towards the boy. You have to move the pivot a little to the left, because it was here originally, so that's how much he moved it. Yeah, Lynn, you don't look happy. What's confusing you?
So the whole seesaw.
Yeah.
Why the girls have the seesaw, but the boys don't the without seesaw.
The way the seesaw and the girl on the right, they're trying to make it turn clockwise. Then on the left, the boy is trying to make it turn anti-clockwise. And these must be balanced. So this turning force here should equal this one plus this one. So that one's the boy, that one is the weight of the seesaw, and that one is from the girl. And I'm just using the formula turning force equals force multiply distance. We'll do more examples. Okay. Can you copy that one down? We'll do another one. Is it okay, Zach? Are you checking something?
Times everything out and still get the right answer.
You multiply it in the 9.81? Yeah, so you should obviously get the same answer.
Don't know what I did now. Don't know what I did wrong.
Let me just, sorry, just get the questions open. What are we on? Principle of moments, isn't it? Yeah. Okay. You're writing this down, Diego? Do you need a minute?
Just 2 seconds.
Yeah. You haven't figured out your mistake yet, Zach.
Yeah.
Continue. Are we all just waiting for Diego? Is that what we're doing? Okay.
Alright.
I'm rushing you, Diego, but I want to get the other examples looked at. Sorry. So we did the first one. Okay. A 100-gram meter stick. Oh, it's in the other room, I guess. So what you have here is a 100-gram meter stick. Do you know what a meter stick is?
A stick that has length 1 meter.
Good. And it's also marked. So it's marked there at 0 and then marked at the end at 100 centimeters. You know. And there's 2 strings, one at 25 and one at 90. So what you have here is a string, and then this is at the 25 centimeter mark. And then you have another string here, and this is at the 90 centimeter mark. And then of course you have the weight, and the weight will be 0.1 g. And where would the weight be? Well, that should be at 50 centimeters, the center of the stick. Okay. And my question is to calculate the force here, which I'll call T for tension. And this one's also a tension. I'll have to use a different letter. We'll call it S. And my question is, what's T and S?
T1.
Or T1, T2 as well, yeah. Now, what I didn't say in the last example, but it's useful to know here. Well, let me actually ask you a question. Where is the turning point? Where's the pivot? So you have your meter stick and you have it hanging from 2 strings. Okay? Where's the pivot? Where's the turning point?
In the middle of those 2 points.
Yeah. Okay, so we have one person saying the middle, and you're saying at the 2 strings. We can only pick one. We have to pick one.
So I mean, on the middle of the 2 strings, not the middle of the.
Oh, it's like somewhere up here.
No.
Down here.
Somewhere there, but like in between,
Between
not the
25.
handle.
Oh, not necessarily at the 50. So like it could be like here.
It has to be between 25 and 90.
Okay, that's one place. Any other ideas?
Wouldn't it be at 0
Okay, you're going to put the turning point here. Good. Any other ideas?
or 100?
Okay, good. Yeah, all right. Yeah.
Oh no.
You've changed your mind.
Yeah.
Any other ideas?
Oh. Wouldn't there be more than 1?
Depends what you mean. Tell me more.
Well, if you have 2 forces like that,
Mm.
it doesn't.
Well, the seesaw had 2 forces as well, didn't it?
No, yeah, then.
You're sticking with your original answer. Yeah. So look, the good news is you're all right. Everybody's correct. When the system is in equilibrium, you're actually allowed to consider the turning point as being anywhere you like. Now this is like a mathematical trick. It's kind of a little bit strange because in the last question you naturally imagine the turning point here, right? But technically the turning point is wherever you want it if it's in equilibrium. It doesn't matter where you put it, you'll get the same answer, which is quite amazing actually. So if Diego did a calculation where he put the turning point here, he would get the same answer, the exact same answer as Zach, who maybe might put the turning point here. So this is a useful trick. If you can put the turning point anywhere, then you should put it somewhere that's convenient. So now, what is a convenient place for the turning point? Well, it turns out it's very useful to imagine the turning point being like here. So, on one of these strings. Okay? So if this is the turning point, I'll write F for fulcrum. Will this force turn it clockwise or anti-clockwise? Clockwise, very good. And this force? Anti-clockwise. Yeah? And this force T does nothing to turn it. Why? We talked about this in the last class. Why does the T force not cause a turn?
Because it's in a direction of the turning point.
Yeah, because it passes through the turning point. Remember my example with the door? Yeah. Yeah, you can't cause a turn if the force goes through the point. Yeah, you remember that? Yeah? It's okay? You look a little confused, or you're not. It's okay. It's okay. So look, let's do the calculation. How much is the clockwise turning force? What's the distance? This distance. What is it?
50.
No?
50 minus 25.
Yeah.
No,
It's
25 times 0.1 g. That's the clockwise, and that should equal the anti-clockwise. What's the anti-clockwise? 0.
90 minus 25.
90 minus 65, is it?
Yeah.
0.65 times, and what's the force?
0.1 g.
No, we've done that one. It's this one.
A.
It's S. S, yeah. That's the force. I called it S. The A just was for anti-clockwise, just to remind me. Guys, is this okay? What I find interesting, every year the physics students always have trouble with this lesson. I'm not sure why.
It's very hard to visualize.
I think it's a visualization problem.
Intention, would it also include the component, the reaction force of 0.1 g?
No, because you're just looking at the effect of that force. Yeah. We've already considered the 0.1 g on the left. Come on, give me your questions. Don't just look so confused. Go on, Lynn, yeah?
Why the mass is 65?
Yeah, why is it? Because it's the distance from the force to the turning point. So it's the distance from, where's my pen gone? I can't see it there. Here to here. And this is at 25 and this is at 90. So that's a distance of 65 centimeters.
90 minus 25.
Yeah. Is that okay? Is it? Is it really? I don't know. Should I believe you? Okay. So what's S here, please? 28? 38. 384?
0, so 3,84.
Yeah. That's Harry gave me that. Now, who has a smart idea for getting the T? How could I get the T?
The same, but putting the.
Yes, you could do that. There's even an easier way, though. But you're right, you could do that. You could put the turning point at S. Yeah. But an even easier way. Now, I'll remind you, the system is in equilibrium.
So
Oh, then
it would be that
Yeah.
plus A equals 0.1 g.
Yeah, you keep saying A. It's not A, it's...
Or A, I mean anti-clockwise.
Ah, yeah, but what's the force? It's S. It's S. So you could...
Okay, yes,
yeah.
plus T.
T plus S equals
0.1 g.
0.1 G. And we know the S already, don't we?
Yeah.
So now we have our T. Yeah? No. You forgot the 0.1.
Oh yes.
That's what you did. Yes?
I lost it, so I just cleared the answer.
It's 0.981 minus 0.0384, giving you 0.796 or something, is it? No, sorry, I was looking at the wrong way. What is it?
9426.
0.943 newtons. Harry, this is okay for you, it looks like. You're happy with this, yeah? Yeah. But Lynn, I'm not so sure. Happy?
I read class, I'm so sure, but I'll figure out next class.
Okay. Diego?
I'm getting there, yeah.
You're getting there, okay. Zach?
Yeah.
Is okay? Is okay for you? Not okay. Not happy with it. And
That's a good thing.
and Gina? Is okay or not okay?
Well, instead of looking at the rotation, what do you call it? The
Rotation, clockwise, a moment, yeah.
It's now up and down.
Yeah, I said the up force is equal to the down force.
So that's
Yeah.
the two strings.
Yeah. It's what it was in the equilibrium definition. Is this okay or not okay for you?
Wait, then what's
So
with the
both-
0.1 and what's 0.1 d? Where does that come?
Because
That's the
the
weight.
total force downwards.
Oh, okay.
Do you have the definition of equilibrium in your notes?
Yeah.
Do you see one of the three formulas is that the force up
Yeah.
equals the force down? Yeah.
Okay.
Regina, is it okay for you? What do you think? You think so? We'll do another example, okay? Every year students get confused by this lesson. I'm not sure why. I don't know why. Let's have a look at the next one. You need to write this down, Zach. Harry, you saw this before, yeah? You studied this before? Yeah. Go on. What are you thinking?
Well, we've studied something like this, but it was totally different.
Totally different.
Like the way we're calculating things. But I don't.
How could it be totally different?
Not totally, but we don't have this parts like that. We have kind of this.
Yeah, I also did it
Long time
a
ago.
while ago.
I don't know about this. You'll have to show me if you find your notebook from school. All right, we'll do another example.
Each person
Do I want to do this one or is it too hard? Let me think. Ah, okay, so, all right. I just made the story a little bit funny. Right, so he's bench pressing 100 kilograms. So he's lifting a weight of 100 kilograms. And he should have his hands symmetric, but instead he doesn't.
No, he has.
Oh, he should have the weight symmetric.
Weight, yeah.
Yeah, but instead he doesn't. So he puts the 40 here and the 60 here, which of course is huh?
Yeah.
40 and 60. His hands are 10 centimeters from either end, and it's 1 meter. So,
So the bar has no mass.
yeah. Well, if you're if you're lifting 100 kilograms, you shouldn't be worried about the mass of the bar. Like, it shouldn't really have much of an effect on you.
How much are you?
It's usually 20 kilos.
It's not, is
Yeah,
it?
yeah.
Just the bar.
What?
Yeah.
Are you sure?
Yeah, or 22 pounds. Yeah.
Come on, guys, don't pretend you know what you're talking about. Are you serious?
I did powerlifting and quite certain.
20 kilograms?
Yeah.
Okay.
Yeah. Like ones that are not
American ones are 22.3 pounds.
Wow. Okay. I just always thought they were like no mass. Okay. Well, this one is fiber, carbon fiber. It's no mass. Right.
New
So
one.
it's a new one. Yeah. So his two hands are. It's very similar to the last example, right? Because you have two forces here which aren't equal. In fact, you know what? Let's call them R and S this time. Reaction force, technically. And this distance here,
10 centimeters.
10 centimeters. I'll put it in green. 10 centimeters. And this distance here,
Same.
that's 10 centimeters. And therefore, this distance here is 80 centimeters, isn't it? Okay. By the way, which will be bigger, R or S? Which will be bigger?
Yes.
S will be bigger, won't it? Yeah. Now, I'm going to do this one, but I think it would be better for you if you first just give it a try, because it's so similar to the last one. See if you can calculate it. The R and S again. Yeah. And I'll put the other forces in here. This is 40G. And this one here is 60G. Okay, see if you can do it. You got it finished, Harry? No, okay. Are you stuck? Oh, okay. I thought these were easy for you. Not too easy? Okay. Okay, we should be finishing it up if we know what to do. Anybody get an answer? Oh, it looks like someone nearly does, okay. Zach, you're looking a bit confused by this. Yeah. Every year, I don't know what it is about this lesson. Just the two most confusing lessons in mechanics, in my experience for students, are projectiles and turning forces. I understand for projectiles why it's difficult. I never understand why this one is difficult. I don't know. All your faces look so worried and troubled. Okay, well we have a look at it now. Yeah? Yeah, we'll look. Okay, so where do we want to put the turning point? Let's put it here at the left hand. Okay? I suppose that's actually his right hand. This force, will it make the system turn clockwise or anti-clockwise?
That's clockwise. No, that's clockwise.
Anti, bro.
Why is it?
Which is it?
It's lighter than the other one.
No, it's
No.
No?
Well, everything's balanced, so that doesn't really matter. My question is, this force, is it trying to cause a turn in effect clockwise or anti-clockwise?
Yeah. That one, like anti-clockwise.
This one's anti-clockwise.
Yeah, because the thing is trying to go like that.
It's trying to turn this way.
Okay.
Yeah? Okay. This one no effect. This one?
That's.
Yeah. Go on. What is
Oh,
it?
that's clockwise.
It's anti-clockwise, thank you. Yes?
Last one's clockwise.
And the last one is clockwise. Yeah? Yeah?
Yes.
Alright, so how
Yeah,
much...
yeah.
We agree, huh? How much is this turn in effect, this moment? It will be 0.1 times 40g. Yes? But be careful, we have to write plus 0.8 times s. Because those two forces are working together to turn anti-clockwise. And that should cancel, balance, the force causing the clockwise.
0.9.
Which is it's 0.9
60.
60g, isn't it?
Yeah.
Like this.
Do you not have to show negative symbols for the change in direction?
No, we've achieved that by having it on the other side. Because if you think about it, if I move this to so
Okay.
that's actually already in the formula. Guys, is that okay?
Solve for S.
Are you sure? So yeah, if we solve for s, we'll get 0.9 times 60g minus 0.1 times 40g over 0.8. So then s equals should be pretty like big, like I don't know, 400 and something newtons.
600.
600 and
13,13.
okay,
613.
613.
Yeah.
613.1 trade,
Yeah. 1, 2, 4.
which is roughly 1613 newtons.
And then you just make that equal
Yeah, well then you say or plus s equals what?
100G.
100g. Yeah? So then or will equal, what's that, 981, isn't it? Minus 613.1 trade. So then
367.
you get or equals 367 newtons for the or. Is that, like, I mean, there's not a lot here. It's just like what you do in maths. It's just two linear equations, you know, or and s, x and y. Yeah, it's okay.
It's just like everything we've done up till now doesn't have a rotational force, so it's hard. We're thinking in terms of moving
X and
left
Y,
right,
yeah.
left and right, up and down.
So
Yeah.
we don't need to put the minus on it because the s is minus 6 minus 1. So we don't need to.
No, we don't. Where? Just a sec. Where would the minus do you think should be?
S.
In the answer for s.
Yeah.
Oh, here. Interesting. Why do you think there should be a minus here? Like this.
Well, it depends on.
Oh wait, your calculator.
It shows that, I think.
It does? Are you sure?
Well,
I
did you put
don't
negative
know.
9.81 or did you put 9.81?
The G is 9.81, yeah.
Then how do you get a negative?
I'm intrigued. I want to see what she's typing. Show me, show me. Yeah. Oh, you're typing it backwards. No, look. No, wait, stop, look. You should start with 0.9. You're starting with 0.1. That's the reason it's minus. Yeah, the R and the S should be positive, for sure.
Yeah.
For sure. The only time, if the S was negative, what that means is I drew the picture wrong. The S is pointing down.
Yeah. Well, I mean, if you sum in minus 9.8.
Yeah, but
Then
I've already considered the sign. I've already considered the sign by putting it on the right hand side. Is okay now or not? It's okay? Oh, what's wrong with you? What's wrong?
It's okay, I'll just take a look at it later. Yeah.
I just would love to know one day what it is that my students are thinking when they look at this and they get so confused.
I say everything up till now we've only thought of moving left, right, up
Yeah,
and
but
down.
it's only clockwise, anti-clockwise, you know. Is the problem that you have no imagination? Is this the problem, maybe?
Too one-dimensional thinking.
Are you watching too much TV? Is it? I don't know. What?
I guess everything up till now has been straightforward. So
Yeah, but still, like I said, it's only clockwise, anti-clockwise. You know. Yeah. Mm. I think we definitely want to make sure you practice those questions tonight.
but
For
there's
this
only
one.
two, so only two.
There's only two?
Isn't it? You said for the next one?
No, that was
No,
for,
no, no.
yeah.
Yeah.
How many's for this one? I think there'd be more than two.
There was quite a lot.
Yeah, because it's a common exam question.
6, 9, 12. Plus we finished the even the
Wow.
odd
Yeah.
questions as well.
How many for this lesson?
12.
12.
Okay, so look, before you start, let's get the ball rolling. I'll just do the first one to get us warmed up, okay? Because I'm looking at your faces and you look like you need another example. So, Dorian, could you read the first one to me? What have we got going on?
A uniform plank of wood AB of mass 20.5 kilograms and length 2.35 meters is placed on a pivot located 1.31 meters from end A of the plank.
1.31 meters.
From
Okay.
end A. A child of mass 18.6 kilograms sits 0.823 meters from end A.
Oh, goodness sake. Right, sorry. He's here. I'm drawing him as a box. And what do you say? 0.8
23 meters.
meters. And what's his mass?
18.6 kilograms.
18.6 kilograms. Okay.
Determine the position of the second child from end B
Yeah.
of the plank if this child has a mass of 25.3 kilograms and the plank is balanced in a horizontal position.
Yeah, so it's in equilibrium. So the question is, what's this x? Okay? Now, before we start, let me just get the other distance. So 2.35 minus 1.31, that's 1.04 meters. So the distance from here to here is 1.04. So that means the distance from here to here is 1.04 minus x. Okay, and we have this distance, don't we?
Yeah.
So I would like this distance here, which should be, oh, this should,
It's 1.31. Yeah.
1.31 minus 8 point, yeah, 823, what's that?
0.487.
487 meters.
No, that's not right.
Yes, it is.
Is it?
1.3, it looks right, yeah, 1.31 minus 0.823, isn't it?
So,
Is right? We're fine?
yes, we're fine.
Okay, so look, we have a force here, yes,
90.6 G.
and we have a force here. Oh, and there's the 20.5, which is going to be
The actual weight.
the actual weight. What? Oh, yeah, can you do 2.35 divided by 2? I want to get the middle. 2.35 divided by 2. What's that?
1.175.
1.175. So that will have it a little bit
To the right.
to the left,
Oh, the right. Yeah.
isn't it? If this is here to here, it's 1.31.
Yeah.
So the weight would be, my picture's really off, the weight would be like here, isn't it? Right?
Yeah. The distance in between is 0.135.
Ooh, this is a messy picture. Sorry. What distance are you giving me? The distance here, is it? This little distance?
0.1.
Because you did 1.31 minus 1.175. How can I fit this in? What distance? Sorry.
0.135.
Oh my goodness, 0.135. And this is 20.5 G. This is 25.3 G. This is 18.6 G. And there's one more force in my picture which I didn't draw in. If I only have down forces, the thing should fall down.
The normal force.
There's a normal force here.
Of the reaction.
Yeah. Now, can someone tell me why I didn't consider that in my last seesaw example?
Because it doesn't really affect
Nope.
the problem.
Well, why not?
It went through the turning point.
Because it's,
It wasn't
it's the
equilibrium,
reaction. It's the reaction of the weight of
Yeah.
the object, so like it equalizes.
True, but not the reason why I didn't draw it.
It went through the turning
It went through the turning point, so it didn't matter. Whereas I'm going to draw it here, but it'll probably not matter because again I'll probably put the turning point at the pivot anyways,
Yeah.
so it doesn't matter. So with great care we can get the formula. With great care, let's make this the turning point so we don't care about the or. All right. Okay, let's begin. Clockwise or anti-clockwise?
Anti.
Anti. This one?
Anti.
Anti. The heck? Anti. This one, no effect. This one? Clockwise. Okay, so let's start with the first one. Whoo, distance is 0.487 times 18.
19.
But that was 18. Yeah, 18.6 G. Plus 0.135, you told me,
Yeah.
times 20.5 G. Equals, very good, Harry, equals what? 25.3 G times, what's the distance? 1.04 minus S. Again, we can cancel out the G's, and then we won't do it now. No, we won't do it now because the time. Then, I've done the hard part. This is the hard part. The easy part is then to solve for X at the end, isn't it?
Yeah.
Just a linear problem. Okay. Yeah, this is a normal, like, how many examples did you say there were? 12? So this is a standard exam question. Okay. What I want you to do now for the next 5 minutes, I want you to copy this down and then get started on these. Do we have class tomorrow?
Yeah, 1 period.
1 hour?
Yeah.
Okay. Yeah. Okay, get started on these. Copy this down.
Do you want us to do all 12 for tomorrow's?
Well, I think because you're finding them so dang hard, it probably would be a good idea if you could try to get them all done
And the odd numbered questions from last lesson.
Well, do you think? Let's see, depends how much time you'll have this evening. You know. The other lesson was also important for the exam because there were many questions. Can you at least make sure for tomorrow you have the odd questions done from both exercises? Like, you know what I mean by odd questions?
But which exercises?
From both, this one and the one about the
The one we had
momentum.
for today.
Did you have, are all those odd ones finished? Yeah.
After the-
So I need the odd questions done. Odd questions, like 1, 3, 5, etc.
Yeah, because we've done the even ones.
Yeah. The odd ones from this, and the last one was the, you did the even ones in the momentum one, wasn't it? From the momentum lesson too.
Okay.
Questions to do then.
15.
Yeah, but the momentum ones are short, aren't they?
Yeah, and they're all pretty much.
It's like
This,
thing moves,
yeah.
thing moves right, thing moves left. What's the change in momentum?
Easy.
Are you trying these, Harry? Yeah, you finished it? And how about the next one? Working, Zach?
It's just a really long question.
The next one.
Wow. It's about to take it.
Is our picture?
Yeah.
So,
Do we know this from middle to the picture?
Yeah. Yes. Because you know where this is. It's not on the picture, but it's written in the story. 1.31 from here to here. There's 1.31.
Is it? Oh, okay.
But it's not drawn on the picture. And this 20.5, you know, is exactly in the middle.
Oh, the middle. Okay.
Because it's the weight of it, you know.